This is a video lesson on packaging questions. This is a specific type of question having to do with optimizing 3D solids. And an application of that theorem is when you're asked to package a certain number of products together in a way that minimizes the surface area of the package. And often things have to be packaged as rectangular prisms. And we know that the best rectangular prism is a cube, but sometimes it's not possible to package things as a cube. And here's an example of how that's true. Imagine that you had 24 of these soup cans packaged together and shipped off in one box. The way that those cans are oriented, the way they're laid out, changes the amount of packaging that would be required. So what I'll do is I'll take you through 4 different configurations to show you how that's true. And note that when I talk about the configurations, I talk about how the cans are lined up. So 1 by 24 means one can, 24 across. And this configuration is different than the dimensions, because if all of these fit into one cardboard box, the dimensions of the box wouldn't be 1 centimeter by 24 centimeters. Remember that each can has a diameter of 8 and each can has a height of 11 centimeters. So if these fit perfectly into a cardboard box, this dimension of the box would have to be 8 centimeters because that's the diameter of the can. And this dimension of the box would have to be 11 because that's the height of the can. And this dimension of the box would be 24 cans, each one with a diameter of 8. It would be 8 times 24, which is 192 centimeters. And when I find the surface area of the box or the package, it's based on those dimensions. So this gives me an idea of how to draw or sketch or imagine, because a sketch isn't always required, what these look like. And I need an idea of what this looks like in order to find these dimensions. But these are the dimensions that I'll use to find, let's say, the volume of that box, which is area of base times height, or length times width times height. And that works out to be 16,896 centimeters cubed. And the surface area is 2 times area of the base plus perimeter of the base times height. And for the perimeter of the base, because I took my base to be this shape down here, 8 by 192, I added up all 4 sides. I added up the 2 8s and the 2 192s. There's 2 of each, times the height. And the height of that prism is 11. And that surface area works out to be this number. You can pause and try it if you like. But what I'm going to do is I'm going to compare that to a separate second configuration, and then to a third, and then to a fourth. If I, instead of packaging 1 by 24, I package these as 2 by 12, that means 2 cans side by side by 12. I know that it would have to be 12 because I have a total of 24 of them. So if I'm going by 2s, I would need 12 rows. And that means that the dimensions of the box that these have to fit into now, with 2 cans, one next to each other side by side, each one with a diameter of 8, that would make that dimension 16, the height 11, and this would be 12 times 8. It's 96. And if you want to pause and try to find the volume and surface area of this cardboard box, you'll find that the volume is the same as it was originally with the 1 by 24, and that the surface area has changed. It's quite a bit lower. So there is definitely an impact on the way we configure the cans to what its total surface area is. It's quite a bit lower here. And another way I can configure 24 cans is to have them 3 by 8. Now notice that in my configuration, 3 times 8, that product 3 times 8 is 24. It's because I still have a total of 24 cans. And when I find the dimensions, again, this is going to be 3. 1, 2, 3 cans next to each other. 3 8s is 24. The height is still 11. And now the depth, or depending on what you want to call this, is 8 times 8. 8 cans, each with a diameter of 8, that's 64. And again, if you want to pause to check your volume and surface area to see if you've done it correctly, the volume is the same, but the surface area is even lower. So that rule that we talked about earlier is that the closer I get to a cube, the more the dimensions are like each other, the lesser the surface area will be. And so you can imagine that in configuration, which is 4 by 6, which is even closer to a cube, it's more square-like. the dimensions of the box work out to be 32 by 11 by 48. And again, if you want to pause and check your answer, the surface area and volume of this are, again, volume equivalent, the exact same. There's the same amount of stuff in the box. But the area of that box is, again, even less, 4,832 centimeters squared. So is that the best configuration? Well, it's the best of these 4 that we've seen. And if I try to go past that, like if I try to put another row, I can't put 5 rows because 24 cans isn't divisible by 5. There wouldn't be an even number in each row. And then if I tried to go by 6, it would end up being 6 by 4. It would actually be the same configuration as this, but rotated 90 degrees, if you can imagine that. So then I'd get back to an answer that I already have. So is this the best one? Well, I claim that it isn't, because what I can do is often work in another dimension. Like here, I've got 1, 2, 3 by 4, that's 12 cans. But if I stacked another 12 on top of them, and I put a box around that, the dimensions of that box would be, well, this is 3 cans across, each with a diameter of 8, that's 24. This height is 2 cans tall, that's 11, and this depth is 4 cans times diameter of 8. So the dimensions of this box that would be needed to fit this configuration would be 32 by 24 by 22. And if I found the surface area and volume of this configuration, the volume again works out to be the same, as it should. The box has the same number of cans in it. The surface area works out to be even less than the previous setup. This is actually the best one. But there's a better way to tell that it's the best one than having to go through and solve for the surface area and volume of each one, because our rule was that we had to have something that was the most cube-like. And the way to check that as a shortcut is to check to see if the dimensions are as close to one another as possible. So if you look at the largest dimension that existed and subtract the smallest dimension, the smallest difference between those two would be the best. For instance, in this configuration, the 1 by 24, the largest dimension was this one here. It was 192. And the smallest dimension was the width, which was 8. That difference is 184. It's a big difference. If I looked at this one, which was better, the largest dimension here was this length here, which was 96. And the smallest dimension was the height, which was 11. It wasn't this one. This was 16. It's not the smallest of the 3 dimensions. That difference is 85, which is still quite large, but a lot better. And the configuration that we just looked at, the largest of those 3 dimensions is the 32, and the smallest of them is the 22. The difference between those two is only 10. That's a very small difference. And so if I wanted to check even another configuration and say, well, I could have maybe gone 4, stack 4 cans one above the other, and go 2 by 3. So this I would have said is 3 by 4 by 2, 3 by 4 by 2, and this is 3 by 2 by 4. Notice that the order in which I say them is important, because the cans themselves do not have the same 3 dimensions. They're 8 by 8 by 11. Not all 3 dimensions are the same. So is this configuration better than this one? Well, there's a quick way to check. I can look at the largest dimension here, 44, the smallest one, and check to see if that difference is bigger or smaller than 10. And if it isn't better than 10, then it's not a better configuration.